Good morning, everyone. Just like the chair said, I am Oliver Ozioko. So I'll be presenting today our work on inductance-based flexible pressure sensor for assistive gloves. So these are some of the things I'm going to talk about today. First of all, I'm going to talk about the motivation, then the existing assistive gloves, sensor structure, the fabrication steps for the spiral coil, then the fabrication steps for the ferromagnetic elastomer, then some images of some of the elastomers, and sensor characterization and results, then conclusion, and then acknowledgement. First of all, the assistive gloves in this particular research work that we are looking at is the one that will help deaf-blind people who cannot see or hear at the same time, who have dual impairments. So the assistive glove is actually to help them for their communication. Basically, this category of people, because they cannot see or hear, they have different methods that they use for their communication. And these methods depends on the nature of their impairment, whether it started from birth. But these gloves are not from people who are congenital deafblind, because for people who are congenital deafblind, they do not use, they do not know language, and it's hard to teach somebody who has not even learned anything about language how to communicate that this is letter A or B. So it is particularly for people who have acquired deaf blindness, and for these categories of people, they have already learned language. So the people who became deaf as a result of accident or as a result of illness. So, and the different methods I have presented here are the different methods that they use depending on the area where they are from. Different countries use different methods of deafblind communication. So, for instance, the one we have on the right, the A, is British Deafblind Manual Alphabet, which is a method that they use popularly used in the UK by deafblind people for communication. So the points that you see there are sort of mapping of the areas of the hand where they are touched. Because for these people, how they communicate is that people touch them to say this is A, and they already know what these things mean. People touch them on particular areas of the hand to say if they touch a particular area, they know this place is A, this place is B, this place is C. They are very familiar with it. And from the interview, because I interacted with some of them, and it's not easy for them to change the method they are already using because of their condition. So they are happy to have this smart glove developed for them. So the other one is is a LOM deafblind manual alphabet. The other one is the Malossi. For each of them, there is one for single touch where they just touch a particular place, and there's one for some letters that they sign on the hand, and there's the other one, the multi-static touch, which either you can use two hands or touch multiple points. That's the multi-static touch points. And these are some of the assistive gloves that have been developed in the past, and most of them use commercial and rigid components. So our idea is to develop something flexible so that it will sort of conformable on the glove and on the hand when they wear it, so that they will be able to use it for communication. So integrating these sensors on those points where they are meant to be touched to make it easier for them so that they can wear the glove themselves and then touch and then send messages to mobile phones or mobile devices or interact. It's sort of an input device for an interface for them to interact with the world through communication. So the idea here is to develop it in such a way that there will be touch and vibration at these points, because you're not going to change. If they are sending message, they're going to touch it themselves to send, and then when they receive message, they will receive in form of vibration. So instead of for somebody touching them, there will be vibration at that point. If they want to send this, they touch the same point. So the idea is to have a touch sensitive actuator that is on a particular point that will enable them, when they want to send, they touch it. When they receive message, it should also vibrate. So there should be a touch sensitive actuator. That is actually what we are looking at. So the idea is to have this touch sensitive actuator, and this part of the work is considering just the touch parts, the touch sensitive parts, which we are considering using inductance based pressure sensor, because the coil of the electromagnetic actuator is to be used also as the touch for the touch part. So the idea is to have an electromagnetic actuator which uses a coil for actuation and a coil for sensing. So that is why we are considering inductance-based pressure sensor. So we have an electromagnetic ferromagnetic elastomer which will be attached on the coil, so that by the time you press the coil, these particles changes, they go closer to the coil, and as they do go closer to the coil, the inductance of the coil changes, and with the same coil we'll be able to also create actuation through magnetic interaction by introducing a permanent magnet, which we could also be flexible. So that is the main idea, and that's the sensor structure over there. And what we have done in this direction is to first of all develop a flexible coil on polyimide. So we have a polyimide sheet which we developed a flexible coil using LIGA process. I think it's a German word, Lithographie Abformung, Galvanoformung, something like that. So that's the LIGA process, which is a micro molding technique for microfabrication technique. So this coil was developed in such a way that it will be flexible, and then when you introduce the elastomer, which is also flexible, made with an elastomer, you should be able to sense when it is touched. So the development involved, first of all, the first step, we got the polymer sheet, and then on it we used the metal evaporation and coated it with a fed seed layer, and then gold on top of it. We used nichrome and then gold on top of it, and then spin coated photoresist on top, is a 4562, because we are intending to get something about 17 micron thickness of the coil. So we want to use the photoresist as a sort of mold for it, so that when you plate it, you should be able to plate only the part of the coil that is required. So the next step was to expose it. So the exposure using the lithography, and after the exposure, then we have the pattern of the coil that we want using we used a dark field mask for that. After the exposure, then what we did was to electroplate now the coil. We made contact with the seed layer itself, and then from there we electroplated, and only the part of the coil that was exposed was plated. And then we of course removed the photoresist, and then etched the gold. And etching the gold, we control the ratio that because the thickness initially was just about 20 micron of gold, so we made it in such a way that after etching for a few seconds, then the layer that is just the seed will go out, and then we'll have only the pattern remaining. So, and after that, the next thing was to mix ecoflex, 2 portions of ecoflex, and use that to realize a ferromagnetic elastomer using iron powder. So the iron powder was mixed in different ratios. We mixed in 1:1, 2:1, and 3:1, which is iron powder, ferromagnetic elastomer to ecoflex to iron powder. That's 1:1, which means the one on the left is for the ecoflex, and the one on the right is for the ion particles. So they were mixed in different ratios just to see the performance of each of the elastomer when you integrate it with the coil. And why we stopped at 5:1 particularly is because we were considering that having much more, if you introduce so much of the ecoflex, the ion particle becomes so small that it is not really significant in the entire ferromagnetic elastomer. So we mix different ratios, and we realized, after curing it, we realized the ferromagnetic elastomer, which is 1 cm in diameter, because it's the same with the diameter of the coil, and then about 1.5 millimeter thick. So we are using this just to see how the effect of the particles actually on the coil, how it responds to, so that when we are now going to integrate the actuator part, because like I said, we have 2 parts, the sensing part and then the actuation part, which are going to be integrated together. And these 2 parts, we are saying that by the time we examine this and find out which of these ratios of the elastomer gives better results, then we will use that to realize the actuator. So these are some of the same images of the elastomer. What we've particularly noticed is that because of the immiscibility of these of the two of them, when you keep it to cure, it settles down. So there's the sort of dense side of the elastomer. The elastomer has a dense side, and then a side that has less, sort of a gradient when you view from the edge, it's sort of a gradient of the particles because it settled when it was curing. And after this paper, we continued the work by checking other ratios, by introducing more. Each of these ratios we try to also check. Like 1:1 is equal ratio, then we have 2:1, and then later we did 1:2, also did 1:3, and 1:5. And for 1:5, after 1:5, we noticed it was difficult to even mix there was not enough ecoflex to mix the ion particles, and we stopped also in 1:5 because it was not sufficient to mix it. So we also checked further. That's not in the paper, but that's something that we did after the paper. So the testing of the elastomer, when the elastomer was first integrated, the inductance of the coil was checked, and after that we integrated each of them to the coil to find out actually if bringing it closer to the coil changes the inductance of the coil. And for that, as expected, the inductance of the coil, for the ones that has higher particles of the ion particles, higher amount of the ion particles, there is more, it gives more inductance, and of course the Q factor was also higher since they are related. So we also checked how flexible each of them, because the more you introduce the ion particles, you find out that it's possible that it becomes very stiff, that you're not able to even press it again. So we also check to find out how stiff these elastomers are. So, but after this work was submitted, we also continued. Like I said, we had some other elastomers which we compared, and in that case, the one that had the highest ion particle, which is particularly not that ratio, it was not used in this work, which is 1:5, which had 5 ion particles, and then 1 for ecoflex in terms of the ratio. That one it was very, very, very stiff. That had the highest elastic modulus. In that case, we examined the elastic modulus, but in this case, what we checked particularly was just how much these elastomers are able to be pressed by checking the distance that they move when they are compressed. The compressibility we had a load cell, and then on the load cell we had a movable and controllable a probe, which we controlled through a lab view program, and with that we were able to check which of them was compressible, and we found out that from this that the 1:1 had the highest change. So also here for the characterization, we also use the same setup that I showed earlier to check how much they are able to respond. With the sensor is now able to respond to pressure. And if you see 1:1, 2:1, 3:1, and 5:1, this now represents the response of the sensor itself, not just the elastomer, because the elastomer is now integrated on the coil. And for 1:1, we noticed it had a higher change. And after the submission, like I said, the further work that we carried out after this also showed that those that had more ion particles were able to give better response, which I believe is because of the interaction of the ion particles. So they have more interactions. The ion particles have more interactions with the coil because of the density. These I've already summarized. Thank you. I acknowledge those people who contributed to the research. Thank you very much.
Thank you.